Alright, we are going to examine another statically indeterminate situation. Now the structure that you see on the image right now looks to be just exactly what we've done before back in the previous lesson that was called example 4.2. We had a fixed end at the left, free end at the right, a homogeneous bar, two different concentrated loads. So the axial force varied from 40 kips in compression from C to D, and then it was in tension 30 kips from B to C, and then it was just hanging out for free out here at A. And given this 18-foot long, 1.5 inch diameter steel tool alloy member, then under those loading conditions, then it's shortened as a net of 0.0328 inches out here at the free end. What we're doing in this example is now to fix this end such that delta A in reality, by the time we're done with all our analysis, must be equal to 0, that doesn't displace. And there's a variety of ways that we might analyze now this statically indeterminate system. You'll see in the Philpott text an approach that I call a highly mathematical and very rigorous kind of approach that is very good, but sometimes it's not as easy to visualize how to set up the constraints as opposed to what we're going to do here, which is called a relaxation technique. And it fits very well with the kind of thing that you see here. So let's do something kind of important here to make sure that we've got everything set up right. And that is, this shaft now has two fixed ends. And that's hard to draw here in this perspective drawing. So what I'm going to do is I'm going to shade in that end, and then I'm going to put a little label that says fixed. And of course, from a side profile view, what we're looking at is this one down here. And this relaxation technique is going to do the following kind of thing. We're just going to represent the rod as just a single stick here, and then we'll put on, indicate that we've got our loads going on there at 70 and 30. And what we're going to do is relax the system by getting rid of this entire constraint that's over here at the right. Right? Not the same structure anymore. Right? So removed one reaction, and we left, that remains, then we have a statically determinate system remaining. That's critical. That's what we set up. And then we're going to impose the actual loads, and we're going to take a look at the displacement that has happened in this primary system due to the actual loads. Right? And we've already calculated that, and that displacement, that delta A0, is equal to this 0.0328 number. And that is going to the left. I'm not going to worry about signs just yet, because sometimes that's where that sort of more mathematically rigorous thing approach is sort of confusing. So we've had that thing shorten up a little bit, and then what we're going to do is we're going to replace, we're going to get rid of all the real loads, and we're going to replace our fixed end such that we have this reaction here at A. And in order for this to work right, what has to be the case is that we started in the real system with delta A was going to be equal to 0. We have in the relaxed system with the real loads, we have this shortening, and we're going to have to pull this out, right, this delta A, and this is a little bit awkward for terms of the symbol. Well, I'm going to call it AR for displacement at A caused by now this unknown reaction value R, and the superposition of these two has to be equal to what we originally have. So what we would call here the compatibility equation is going to be that delta A no other subscript, the actual delta A is going to be equal to the sum of delta AO plus delta AR. And we know from the given constraints in the original system that delta A has to be 0, and then so that makes delta AO be the opposite of delta AR. One shortens, one elongates is what's going on there, right? So minus delta A0 has to equal delta AR, and delta minus A0 we've already calculated. If we haven't done it yet, then we're going to have to go and do all this work here for this first part. And we also need to somehow establish what our sign convention is. So we'll say to the right is positive. So delta A0 was to the left, that's a negative, so that's a minus 0.0328 inches has to equal our delta AR. And of course becomes a positive number. Something that we could have actually just observed directly in this very simple situation here of the mathematical combination of the two. Those two displacements have to be equal and opposite, right? And so we then have to figure out, well, how do we know what delta AR has to equal, but gee, how do we figure out what that is associated with R? Well, now in this case we have a member that is constant cross-sectional properties, that makes it prismatic. It is homogeneous, all the same material, so it's not a composite member, and that means that the force displacement relationship for the entire system with a constant axial force, and we've got constant properties, then is that the deformation in that situation will be equal to NL over AE. And that axial force then would be RA, and our length would be 18 feet, and we've got the E of 29,000 KSI, and oops, I did this in reverse order, but so be it. And then we have, of course, pi r squared. And probably makes more sense to have, instead of 18 feet, have it in inches instead. And let's see, we're going to do this as EA over L, 29E3 times pi times 0.75 inverse squared, divided by 18, divided by 12. The reason I did it EA over L is, of course, that's the axial stiffness. And so that would be RA over 237.2. And let's see, we got kips in the bottom, kips per square inch times square, that's just kips. We got inches on the top, so that's going to be kips per inch. That'd be the stiffness deal here. Right? So that's good. And now we can solve for R. And so the R value, when we substitute back up into here, it's going to be RA over 237.2. So now RA equals drumroll 3.0328 multiplied by 7.78 kips. Right now we go look at the axial stresses, right? Because that's what we were asked to do, and that means we need to get the axial force in each segment. So that means we have to be a little bit careful here, because now we're going back to the total system, going back to this one right there, right? And the way that's going to be set up is that we've got an entire system that now has a reaction that is 7.78 kips there. We've got the 30 kips at B. We've got the 70 kips going the other way at C. And so to go get that reaction out at the very end, we're going to have 32.2, well, 22, going to the right. All of the 30, the 32.22, and the 7.78 will equilibrate with the 70. Right? So notice here that what's going to happen when we do the axial force diagram is that it's going to be similar to what we had in the previous example with this one, except for, of course, different. And it differs because we start off with compression at 32.2. We have that big 70 kick up to 37.78. This was 32.22. So now we're in tension. Come over, and then we drop down by 30. This is like shear moment diagrams. And we're left at 7.78, and when you know, we close off right at 7.78, just like we should. So then as you look through that, we can say, it's pretty obvious that given the cross-section is the same all the way through, that then we've got the worst, the sigma max on the terms of axial stress, is going to be in the middle segment. That'd be BC, and then be NBC over the ABC, and that's going to be our 37.78 kips over our pi times 0.75 inches squared. You get our area, or 21.38 KSI, or let's just put this in nice appropriate language here. That sigma max equals 21.4 KSI. In this case, that would be tension. The max compression will be slightly less than that. That's in BC, and that's sort of the answer in terms of maxes. Right? You can go get the N over A for the other segments if you want those. Right? Notice how this is a slight adjustment. It's really the results we had before, except for shifted up. Now, if you didn't have constant cross-sectional properties here, you'd have to come back and use this segmental approach, where each segment was of a constant situation, and the total displacement out here at the end for delta AR would have to be broken up like we did before, and that would be true if the E varied as well. Right? But because it was all homogeneous in constant cross-sectional properties or prismatic all the way, we could, for this one, take this as one block, whereas this one we couldn't because the axial force is what varied along the length.